Back, everybody. We're going to start, we're going to finish up talking about general computer systems. And the point of this video is to learn software terminology and a bit about assembly language. Up until this point, we described general computer hardware, which consists of two sections. The CPU is made up of really three systems. One is the control unit, which is the large state machine that performs that good old fetch, decode, and execute for every instruction to be executed. We also talked about registers, that those are fast storage devices that hold information such as addresses and opcodes. Other registers are general purpose, which can be utilized as part of our general program. And then we have the ALU, or arithmetic logic unit, which is a large combinational logic circuit that performs basically any math or logic operation that an instruction might require. To the right, external to the CPU, is a memory mapped system consisting of the ports, the data memory, the program memory, and the program memory. The term memory mapped here means that each one of these things outside of the CPU has a unique address that can be referenced by the CPU. So in this video, we're looking at software which resides in the program memory. Now, the programmer decides which instructions to place into program memory and their order, if they will repeat, and if some may be skipped. Remember that the CPU has an instruction set which are fixed instructions that the CPU knows how to execute. And fixed here, I use the word fixed because it cannot be changed easily and is designed beforehand. The number of instructions is not going to be changed. So the instructions are decided by the designers of the central processing unit, the CPU. One design method is to design the CPU so it performs a small number of instructions, like 10, 20, 22. The programmer will be able to accomplish any task. It just might take executing many of these simple instructions. That type of computer, that type of design is called RISC, which is Reduced Instruction Set Computer. With this design method, the physical size of the necessary CPU circuitry and components is reduced. So you want to think about building a state machine, and I've got the state diagram here to the left. The fewer states you have, or the fewer paths there, the fewer number of operations you have, you can imagine would make a smaller state machine when you try to build this thing. And yes, a RISC requires a large number of operations to accomplish a task, right? Because you have fewer number of operations to select from, but each executes very quickly since the circuitry is simple. So tasks can be executed very quickly. Now, another design method is to design the CPU so that it has a large instruction set capable of performing many different instructions, basically one instruction for anything that can be conceived. So this type of design or machine is called a complex instruction set computer, or CISC. And again, you want to keep in mind the building of a state machine. Those paths there on the state diagram that I have, if you add another path, a fourth operation to this thing, you can imagine the complexity is going to grow very quickly, a fifth operation, a sixth operation, and so forth. So it would not be a surprise to you that a CISC has increased physical size, but it requires fewer number of operations to accomplish a task. Those operations are relatively slow because of the increased size, but we need fewer of them. The task is still executed very quickly then. And there's no method better than the other. These basically are two sides to the same coin. The ECE430, which we'll be using in this course, is a RISC and has 22 instructions in its instruction set. So now we might wonder, what type of instructions exist? Well, regardless of the computer, every instruction falls into one of three categories. The first category is data movement. A data movement instruction refers to movement of data back and forth between CPU registers and memory, or between two memory locations as well as the ports. The key here is that when data are moved into the CPU, it's to the registers. The control unit and the ALU, they don't store information, just the registers store. A second type of instruction is data manipulation instruction. With data manipulation, data are processed by the ALU. We could shift bits within a bit string. We can add two bits together. We could perform a 2's complement, or we could increment or decrement a binary string. The data are typically stored in the registers before they are manipulated by the ALU. So more often than not, a move instruction may precede a manipulate instruction. And then after processing, an instruction may be given to move it back out to memory. And the last class is a program flow instruction. Here is where we can make the program more intelligent and less like a fancy calculator, only a fancy calculator. We can make the program behave differently for different situations. Think about looping and conditional statements, right? Give it some sort of intelligence to it. Remember that all the instructions, or the opcodes, reside in the program memory down there at the bottom right. They get executed one after another. At some point, at minimum, you're going to need to come back up to the top. You don't want your program to just stop running. A program flow instruction messes with the program counter address, which again tells us the address of the next instruction to be executed. So in a microcontroller application, the programs run forever. I said before that we don't want the program to just stop. For example, you wouldn't want, say, a pacemaker to stop its program once it's been implanted in your chest cavity, right? Unconditional here is that exact thing, where we're just going to keep running. It's like a while true loop, right? Just keep running unconditionally on the program. Conditional, though, a conditional program flow is like we want to change the flow of the algorithm based on certain conditions that exist within the registers. So think about like an if statement or a switch statement. We want to do different things based on different variables, for example. Now let's take a very close look at these opcodes. Every instruction has a unique binary code assigned to it. That's its opcode, and is chosen by the designers of the CPU. Now, we don't want to be programming in binary. Well, I don't anyway. Maybe you do. That's not a lot of fun to me. The concept of a mnemonic is going to help us. Note that the M in the word mnemonic is silent. So it really kind of, when you pronounce it, it starts with an N. Mnemonic. A mnemonic device is a phrase that's often used just in general English, and it's a method to help memorization. So that's the way you can that's funny. That's the way you can remember the word mnemonic, is by thinking of a mnemonic device helps you memorize things. So we're gonna give our binary codes mnemonics. So we're gonna write in the mnemonics, and those will get translated into the binary code. When you avoid programming in binaries and instead programming with mnemonics, you are programming in assembly language. It's one level of abstraction higher than binaries. There are syntax rules to follow, of course, but this is very low level. It allows us to learn computer architecture since we are effectively programming at the instruction level, instruction by instruction. An assembler is what translates the mnemonics to the binaries, so we don't have to. It's similar to a compiler, which you may have used in the past. Some instructions require information in addition to the mnemonic. If I were to give an increment instruction, for example, I would need to specify what exactly I want to increment. That additional information is called an operand. Some mnemonics require no operands, some require one, and some require more than one, like 2. Let's look at some examples. So if I'm going to write a new assembly file, I'm going to write it line by line. Here is one line that I might write. You see move, then some space, SRC, which stands for source in this case, comma, space, and then DST, which stands for destination in this case. We'll discuss the syntax of assembly later, but let's try to unpack this line for now. The mnemonic for this move instruction is MOV. MOV is recognized by the assembler as the move instruction and creates its associated binary string. The required additional information is the source and destination, right? If I'm going to move information around, where is the information currently stored? That's the source. And to where do I want it moved? That's the destination. Collectively, these pieces make up the operand. Notice again that they are separated by a comma. Again, I want to emphasize that the operand is that entire piece. It does not have 2 operands, only one. You'll see in the bottom right, I've written this SRC, source, with an arrow to DST, destination. That means the data in source gets moved into destination. Source is unaltered in a move instruction. The destination, DST, now has the source's data. So this is a nice, convenient piece to express that operation. Here are some more examples. This example is an add instruction. Its mnemonic is ADD, which makes a lot of sense. I like that one. Again, the assembler recognizes this mnemonic and converts it to a binary string. This binary string would be different than the MOV binary string. The add instruction requires 2 additional pieces of information. Where are the 2 pieces of data to be added together? Right? Those 2 again make up the operand. It's one operand, but there are 2 pieces of data within that operand. Now, at first, it might seem strange to denote here the 2 add-ins as source and destination. It's not like it's being moved. But it makes sense considering where the resulting sum is stored. The instruction takes data located at the source address and adds it to that at the destination address and stores the sum in the destination address. The sum gets stored in the destination address. So that should make sense now. That's why we call it the destination. The data at the source is unchanged. So this operation is expressed here as SRC, or the source, plus DST, and then with the arrow to the destination. So the destination, the old destination data is lost in this case. The last example I have here is of an increment instruction. The mnemonic for increment is INC. That makes sense, right? And the operand is only the location of what needs to be incremented. So for the increment instruction, only one address comprises the operand. And we represent the operation like this. What's stored in the destination gets incremented by 1, and then stored back into the destination. That's why we call it the destination. The original value is lost. Right? Now let's talk a little bit about program development. The C language is a very high-level language, which you probably have experience with. We program in C, and the program just seems to work. We don't know the architecture of the CPU or how internal registers are employed to manipulate data. By the way, my programs never seem to just work. I have to really debug, but hopefully yours just seem to work. But eventually you have a working a program, and that version of the program is what I mean here. We don't really, it works, we don't know the architecture or the CPU, the internal registers and so forth. Now, the C compiler is our friend. It actually translates the C code to assembly instructions behind the scenes, so to speak. It will use an assembler to get to the binaries. But we may never perceive the assembler. We just compile and then bam, it seems to work, right? But we're going deep down here. We're peeling back the layers, and we're getting really low level in our class. The assembler, as we said previously, translates the mnemonics and operands to binaries. And something I haven't mentioned here is a linker, which joins multiple source files, like 2 assembly files, to make one unified program. It also brings in information about the memory map and addresses, because sometimes when you're programming, you may not have to concern yourself about where memory is, for example. A linker can bring in files that actually do have that information. The linker outputs a final executable file that is a binary file that's to be loaded onto the computer, the device. And in this class, we're going to start at the low-level assembly language level, right? And as I said earlier, the device that we're going to use is the MSP430. Starting at assembly allows us to get an intimate understanding of data movement, registers, instructions, all this good stuff that we've been talking about. Later in the course, we're going to jump up to the C language, which is a higher level of abstraction. And then from that point, we might work in parallel with C and assembly. Whenever we think it's useful to use C, we'll use C. And whenever we think it's useful to use assembly, we'll use assembly. Nice. All right, so this was a more detailed look at computer software, but still generic. Next time, instead of considering the generic computer system, we're going to look specifically at the MSP430 and dive into that. So that's it for this time. Thank you guys very much.